Okay. So last time we were talking about the Fuchsian group. This is subgroups of PSL2R, which are discrete. Also, before this, I was talking about properly discontinuous actions. Okay, we are talking about properly discontinuous actions. Now, we'll see how these two relate now. That is, so we look at lemma. So PSL2R acts on the upper half space because it is this group of isometries. So any subgroup of it will act on H as well. So a subgroup will be Fuchsian. That is, a subgroup will be discrete if and only if that subgroup acts properly discontinuously. Okay. So Fuchsian groups are just capturing all properly discontinuous actions. Let me prove this. So let us assume the action is properly discontinuous first. So so we want to prove it is discrete now. Take a sequence in the group converging to the identity. Then we have then we will have at each point TKZ will converge to Z. So properly discontinuous action. Properly discontinuous action will imply that TK of Z will have to be equal to Z at some point after some K for all large K, sorry. So we will get that this will be identity. Okay. For K.
Can you quickly remind the definition of properly discontinuous?
Properly discontinuous is so right. How do I say? So you will have a subgroup or you will have a group acting on some set on X. Then take any okay. So the other direction will be, so we are assuming it is a discrete subgroup now. We have to prove it is a properly discontinuous action. So we take some compact set and some point. Then we will look at this set. Okay, we'll look at all the elements of PSL2R such that they take Z0 into K. Okay, so if we prove this is compact, then our one, and we intersect that with our discrete subgroup. So we'll be intersecting our discrete subgroup with a compact set, which will mean the intersection will be finite. Okay, so that is what we want basically. So it is enough to prove that this is a compact set. So this evaluation map is always continuous because of the compact open topology. So this will be a closed set. We now need to prove this is bounded. So this is exactly the set I defined here. Okay. We just need to prove it is bounded now to prove it is compact. I will not do it exactly. I will just say. So since K is compact, we will have so this will be bounded by some m above, and we will have imaginary part of so this will be bounded below. So these two bounds is supposed to imply A, B, C, D are bounded. Okay, I will not work it out. It's just believe me. Okay, so once you have A, B, C, D are bounded, you will get that this set over here, it is a bounded set. It is also closed, so it is a compact set. Then compact set intersecting with the discrete subgroup we had will give a finite set. Okay. So now I will talk about fundamental domain a little. Okay. So what is a fundamental domain? So suppose gamma acts on our metric space X. So a fundamental domain will be a closed set whose interior is non-empty. And if you take any non-identity element and translate interior of C, they will not intersect. And all translates of C kind of make up X. So if you look, we can look at an example. If X was complex plane and the gamma we had was Z going to Z plus 1. Okay. So suppose your set was this, the closed set was this, C, including the boundary. Okay. Then the interior is of course non-empty. And if you take any translate of the interior, it will just move over here, right? It will move here or somewhere else, but they will never intersect this. Okay. Then the last property is, if we look at all of them, if you take the union of all of these, this will of course union of them is obviously C, right? So this is a fundamental domain for this action on this set. Okay. There can be multiple fundamental domains, but this is one of them. For example, just like half 3 by 2, this will also be a fundamental domain. Okay. There can be multiple of them, but we just need one to work with. Another example is X is again C, and your if you take this, this is a fundamental domain. Okay, so your whole plane can be covered by grids like this. Basically, okay. So idea of fundamental domain is it is some domain which kind of has a unique representation. That is, so if you take any point inside this fundamental domain and you apply any non-identity element on it, it will end up somewhere else. It will never be inside the set. Only issue comes with is like on the boundary there are multiple representations, but that will happen with any set you take. So we are mostly focused on the interior here. Okay. Then there is a thing called Dirichlet domain. Okay, so Dirichlet domain will be take any Fuchsian group, and you take any point in the upper half space. The Dirichlet domain centered at that point will be, so look at all the points which are closer to Z naught, as compared to any translate of Z naught. Okay, so what is it saying is, so suppose we have Z going to Z plus 1. Okay, and E naught equal. Okay, so first we will have a lot of translates of I. So this will be 1 plus I, 1 plus I, 2 plus I, minus 1 plus I, whatever. Okay, then we are looking at all points which are closer to I as compared to any other translates. So we will be looking at all points which are like cut here, minus half, this half. So we'll be looking at all points over here. Right? So these are the only points which are closer to I as compared to the other ones. Okay. So this is also equivalent to looking at half plane. By that I mean you will look at this line, right? Because you will look at this. You will look at the line joining I and minus I plus I. Sorry, minus 1 plus I, and you will have to look at the bisector of that, right? So you will have to look at the bisector, and the bisector will look like this, and you will look at all the elements on this side. Okay, if you do the same for every other point, say you look at this line and you look at the bisector and you take this side and you look at all the intersections, you will just end up with this one box. Okay, so these two are equivalent and they will normally be used together. So lemma. So so we have a lot of fundamental domains, but the Dirichlet domain will be one of them, and it is easy to just specify what Dirichlet domain we are looking at. Like when you say look at a fundamental domain, people can look at different things. But if you specify a point and the group, you will directly get one Dirichlet domain. Okay. The reason it is convex is because it is a intersection of half planes. So intersection of convex sets will be convex, I think. Or intersection of half planes will be convex. That much I can say. Example. So look at gamma equal to PSL2 Z. Okay. Then look at the Dirichlet domain about 2I. This will be, this is I. This is minus half, half. Okay, so this will be the Dirichlet domain for PSL to R. I don't know. Do you want me to prove it? No, I'll just skip this. Yeah, so this will be the end of this course.
Cool.